Let's consider how to draw the chair conformation of cyclohexane. Now cyclohexane is having this structure. Of course we have got hydrogens, two hydrogens at each carbon. Now when you want to draw the chair conformation of cyclohexane, firstly I'm going to draw two lines which are parallel to each other, just like that. And then I'm going to draw, to join these two lines, I'm going to draw one which goes like this, and then I join it to the other on this side. Then I'm going to draw another one which goes down, and then I'll join using this one. So here we are supposed to have equatorial bonds and also axial bonds. So when I'm talking about the equatorial, this has to do with the equator, so meaning these are bonds more in this direction. So I need to have three bonds going up and three bonds coming down, and then three bonds also pointed in these other directions. So then what are we going to do in this case? Starting with down here, I'm going to put a bond that is straight down, also a bond here that is straight down. I'll not put a bond down here because the space here is small. Then the bond here is supposed to go up, and then here the bond is supposed to go straight up. Even here the bond is supposed to go straight up. And then here I'm not going to put a bond that is going up because the space here is small. I'm going to put a bond down. So I've got bonds going up and bonds which are coming down in that way. Okay. So then I've got equatorial bonds and axial bonds. So the axial are the ones which are going up. Now remaining the equatorial bonds, how do you get to draw those equatorial bonds? So if I look at this point, I need to draw a line which is parallel to this one, meaning that that is supposed to go in this direction. If I look at this point, I want to draw something that is parallel to this one. So it's supposed to go like this. Again, this one should be parallel to the bond that I'm drawing at this point, so it's supposed to go in this direction. Then this one should be parallel to the one I want to draw at this point, then it's supposed to go down like that. And then from there, I need also equatorial bonds at this point. I need one each. So how am I going to put those at these points? Well, if I consider at this point, I need to put more a bond that is a bit of parallel to this bond which is here. So meaning I'm supposed to put something which is something like that. And then at this point it should be a bit of more parallel to this one. Then I'm going to put something which goes like this. So these are all hydrogen. So this is hydrogen, this is hydrogen, this is hydrogen, this is hydrogen. So this is how basically we get to write the chair configuration of cyclohexane. So this is going to be it. So imagine this one was another group of atoms instead of it being a hydrogen. So the more these are going to be away from each other, the more stable the compound is going to be in such a case. Imagine this is a methyl group, this is also a methyl group. If they are that close to each other, then they're not going to be stable. So you want maximum distance away from each other for these compounds to be stable. Let's say I want to draw the chair configuration for 1-tet-butyl, 4-methyl cyclohexane. And you want to make sure that you draw the most stable in such a way. Now a tet-butyl looks something like this. It is bonded at this end, and then we have got a methyl. So the first thing first, I'm supposed to draw lines which are parallel like this. I'm going to put something like that, and then I join to this one, and then I also take something like that, and then I join to this one. Now this is 1-tet-butyl. So whatever I take as position 1, let me take this as 1, which one is going to be 2? Let me say this is 2, 3, and then 4. So position number 4 is here. That's where the Matthew is supposed to be. So I'm supposed to have, let me first draw the equatorial bonds, the actual bonds. This one straight up, even this one is going to be straight up. Should be straight down, straight down, straight down, and then straight up. I need to draw something parallel to this one, so it's supposed to go like this. Parallel to this one, so it's supposed to go like this. Parallel to this one, so it's supposed to go like that. Then parallel to this one, supposed to come out like that. And then also parallel to this one, supposed to go like that. And then parallel to this one, supposed to go like that. Okay, so these are the bonds that we are going to be able to have. Now I'm more interested only at position number 4 and position number 1, because that's where we have got the groups. We know the rest of these are going to be hydrogen, so I can even put them. So the first thing that we're able to have, you can see we can either have the methyl group being, so if this is a hydrogen, I can decide to put a methyl group here. I can also have this as the hydrogen, and then I'll put the butyl at this point. So this is a butyl. Or I could have decided to put, let me also write again. So I need to have 4 of these because there are 4 different possibilities. Alright, so it is like this. So for this one, I've put the tet on the equatorial. Now let me still put it on the equatorial, the tet. But what I'm going to just change is the methyl. Let me put it this side. And then let me change the tet. Let me put it on the axial. And then the methyl, let me put it still on the equatorial. And then still let me put the tet on the axial, and then the methyl, let me put it also on the axial. So these are the possible structures. Now just to avoid confusion, let me remove this so that we are going to be able to clearly see. Because my aim is to determine the most stable structure, so I don't need to have these hydrogens because they are all the same. Now from this, which one is going to be the most stable structure? If you look at this structure, the methyl and this one, the methyl is on the axial, this one is on the equatorial. What will be the stability? And then this one, you can see the methyl is on the axial, sorry, the tet is on the equatorial, and then the methyl is also on the equatorial. So when these things, they've got maximum distance away from each other, the more the energy. So this one where you have got equatorial, equatorial, it has got much more higher energy. Not higher energy, because if I talk about higher energy, to mean it to be unstable. So this one is the most stable. Not, let me not again mention the word most stable, but this one is stable. Why? Because these bonds have got a bit of maximum distance away from each other. Now if you look at this one, you have got, this is equatorial, this is axial. How stable is this going to be? This is not that stable, not too much stable. Look at this one. You have got axial and then axial. Which one do you think this is going to be stable? if both bonds are in the axial plane. Okay, because they've got maximum distance away from each other, we expect this one to be stable because they've got maximum distance away from each other. It's going to be a bit of stable like that. Now, what of the first one? We have got this one is axial, and then this one is equatorial. Do you think it's going to be stable? Of course, this is going to be stable. There is more distance away from each other, so this one is also going to be stable. Now, because I've written this note doesn't mean it is not stable. So this one also, you can see this one, this is in the equatorial, and then this is in the axial. It's basically almost the same as this one, which is just the other way around. Okay, so it means it's stable. Now, which one is going to be the most stable? The most stable is supposed to be on the equatorial, where both bonds are facing the equatorial. That is the most stable. So meaning that this is going to be the most stable compound. And then the next, which is stable, the bigger group should be in the equatorial, while the smaller group should be in the axial. So meaning that this is going to be the next stable. Okay. And then the next stable, you are going to have the smaller group in the axial, in the equatorial, and then the bigger group in the axial. So this is going to be the third. And then the least stable, you are going to have both bonds being in the axial. So this is going to be the least stable. So we are seeing that axial bonds are less stable than equatorial bonds. Equatorial bonds are very, very much stable. That's why this is very stable. Here you have got a big group, it is in the equatorial, so this is also stable. Here they have just swapped. It's going to be stable in comparison to this, where both bonds are in the axial. It's going to be much less stable.